Assalamu alaikum wa rahmatullahi wa barakatuh. Very good morning. Yeah, very good afternoon already. Okay, good.
Afternoon, doctor.
So now let me prepare. Okay. So today we try to finish the chapter 1, but still it is actually a lot. So 4 participants. Admit. Okay, let me prepare as usual. QR code actually. Academic. Sharah. QR code. So real analysis. So create one. Save. Okay, so now let me okay, so another 3 students. Admit. So almost 60 students. There's 2 more. Okay, so let me record. Bismillah. Okay, let me start. Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Very good morning, good afternoon. So now let us continue our journey on real analysis in chapter 1. And let me first share screen. And please you do, okay, this one I will make it like this. Please register first. Okay, I hope. Let me on. Okay, next week, I think on Monday, after our class, can I make a quiz from 1 to 1:30, but I will give another 15 minutes for submission. So 1:45, from 1:45. Is it okay? So next week, inshallah, we will make the first another 3 students.
Monday, Dr. Kan?
Monday, yes, Monday. Monday, after our class, you immediately will start. Okay?
Okay,
You will immediately start. So just I'm giving more time. Actually, questions. Actually, I'm not choosing many. Just 2 questions. Okay, 2 questions from the, chapter 1, including the previous lecture notes. Okay. I hope it is the quiz. Usually I make just for the 15 minutes, but of course I give more time of 30 minutes, half an hour, and 15 minutes for the submission. I use the e-pembelajaran. So you will just submit your results in pembelajaran, and I will check later. Okay, so I think Monday, because Sunday we have 2 hours class, and any suggestion on regarding, because still I haven't done yet the quiz, not prepared it yet. So that's why I think Monday better we do. Okay, after our class. Okay, so that's okay. Now
From 1 to 1:45, is it?
from 1 to 1:45. Yes.
Okay, Doctor. Noted.
Actually, as I told you, the 15-20 minutes is enough. But for any case, I am giving another 10 extra time. So 12 to 1 to 1:30, and another 15 minutes for the submission. So total 45. I think more than enough. Okay, because this is not exam, not midterm exam. This is just quiz. Okay, so because quiz, everybody we will make ourselves. Okay, let me start, because here again, this lecture notes a little bit hard to understand, but the main definition, completeness axioms is given quite okay, but examples, provided example is not very good. So therefore I will take from the second lecture notes, and if it is not submitted in the pembelajaran today, I will submit. Okay, what we have to learn for this time, so we will learn this one. We started natural numbers, integers, and rational numbers. We started this, and so if one belong to the n, this one call it, what we call it, inductive. If set is called it inductive, just little revision. If set A is called it inductive, for the natural numbers, actually any set, if any set subset of A is inductive, then actually A is equal to n. That's the main point for this case. But here, please, as I told you, construct to prove their problems, constructing no one waiting. Okay, good. Constructing the set A is very important. Actually, you see how we construct the A is important in the solution or in the proof of the statement. Actually, this one all I can say statements. Okay, so this one already done. This one already done. What is this actually? Yeah, I have shown already. So non-empty set of n has a list element. Also we proved. You see here, constructing this subset A in this form is a crucial. So using this, so every point which is not lying in the set S, you see here, suppose S is a subset but not empty, and at the end we get the S equal to empty set, which is contradiction to this assumption. So it proves that so every subset of n has a list element. Okay, now today actually we will learn a mathematical induction, principle of mathematical induction, and I will get some more proof of the problems from other lecture notes. Here the statement is given in the proper way. Okay, actually the mathematical induction, principle of mathematical induction here is given in 2 ways. One says that suppose that for every n from natural number set, we have statement, a statement Pn. You see, for every n we have the statement. So the statement, if P1 is true and Pn is true, then we derive based on this assumption. If we show that Pn plus 1 is true, then the statement Pn is true for all n. Actually, second is statement, little bit details. So P1 is true for every n. Let Pn be the statement. If P1 is true and P2, P3, and Pn are all true, implies Pn plus is true, then Pn is true for all n. For example, here they give one example, which is theorem. It is given as a theorem. Every natural number greater than 1 may be expressed as a product of prime numbers. Okay, how we prove this statement? Actually, this is the theorem actually. Okay, one moment. I will open the new one. Okay, now let me because if you learn this statement very well, actually you are having very good tools. This mathematical principle of mathematical induction actually one of the strongest method to prove the statement. Okay, that's why it is very important to learn this statement, these tools. So everything is okay. Let me go. You are sharing your screen. Okay. So mathematical principle, what you call it? Principle of mathematical induction, right? The principle of mathematical induction. Today's topic actually is the principle of mathematical induction. Mathematical induction. Well, sometimes we just, without saying mathematical, just induction. Principle of induction. Also, we use the full name is the principle of mathematical induction. So, as you say, to prove this statement, what we should have for any n from n, we have the statement Pn, and P1 is true, Pn is true, implies Pn plus 1 is true. Then we can say that Pn is true, which means the statement is true for all n. Okay. Now, in order to prove to use this mathematical principle of mathematical induction, we have this example actually, very theorem actually. A number greater than 1 which is divisible. What does it mean, prime number? Prime number, in mathematics usually prime number is a number such that it has only two dividers, one and itself. There is no other type of divider. So in other words, a natural number greater than 1 which is divisible only by it, you see, which is divisible only by itself, and 1 is called prime numbers. This is more proper the definition. But in other words, you can imagine that if number cannot be divided any other numbers except itself and number 1, is called the prime numbers. So every natural number greater than 1 may be expressed as a product of prime numbers. This is a statement. Now we want to this theorem actually here it's called in our case actually theorem 1. Every, so just little, every natural number greater than 1, natural number n, actually I can say like this, natural number n greater than 1 may be expressed as a product of prime numbers. As an example, for example, if I take, for example, 126. How can I write it as a how we do? Do you remember? So if you remember the I think this is the from the school, we start from the 2. Actually, prime number starting from 2, 2, 3, 5, 7, 9 cannot, 11, 13, and so on. You have to remember that the smallest number of the prime number is 2. Of course, definitely this number can be divided by 2. So 63. So we can divide by 3. 221. So we can divide again 3, 7. Then we divide by 7, then 1. So 126 equal to 2 times 3 to the square times 7. You see, any integer number can be expressed as a product. Any natural number greater than 1 may be expressed as a product of prime numbers. As a product of prime numbers. So this is just one example. Now, how we can prove it? The statement or theorem. How we can prove it? So for the proof, we assume. Why here they are not starting from P1? Because here n cannot be equal to 1, strictly greater than 1. So therefore, it is starting from the P2. Let P2 statement is true. Is true. Is true. And suppose the second one, we suppose that the P2, P3, and etc. Pn are true, are all true, Okay, all true. Then we will show Pn plus 1 is also true. Now, all true. All true. Now we have to show that if Pn plus 1 statement is true, then if we show that is true, we need to show is true, then we can say, yes, this theorem is true. Okay, now look how they are stating. So actually Pn plus 1 statement, actually here in our case it is n plus 1, number n plus 1. Okay, because p of n equal to n, so Pn plus 1 is n plus 1. So up to Pn, of course, by the assumption, so we have like this, every integer number can be expressed as a product of as a product of prime numbers. So now Pn plus 1, so can be written as, because since this is a natural number, we assume that it can be written as a product of two integers. Okay, so the both greater than 1, so either if n plus 1 is a prime, and hence Pn plus 1 is true if we show that n plus 1 is a prime. How we show? So here we say that it can be written as a product of two numbers. Of course, from here, k should be greater than 1. Should be, both of them should be less than n first of all, because if both of them greater than n, then product and this equality cannot be hold. So this and this hold. From this equality, it holds. Maybe can reach, but cannot be greater, and can reach. So now from the second assumption, both k and m can be expressed as a product of primes. and therefore n plus 1 is also product of primes. Actually, this is not very good proof. Actually, look here, because since k less than n, m less than n, generally we can accept as a proof. So k, so it means k can be written as a product. For example, p1, m1, p2, m2. This is a p1, p2 is a prime numbers. This is a power, and etc. P, for example, maybe I can say here mk, pk, p, maybe pl, ml. Okay, ml. Similarly, the second number is also can be written p1. This one I can say not m1, l, maybe j1, p2, j2, and etc. The product. This is not COCOM. This is product. Just product. So and etc. P, P1, P2. This is PL. This is P, J, K, L, M, N. I can say not exactly same. You know, it should be different. Maybe PI, PI, JI. Okay, JI, PI, JI. So you see here there is assumption. There is assumption. You see, if k and m both of them less than or equal to n, and this assumption p1, p2 up to pn, we by our assumption it is a product of the prime numbers. Okay, product of prime numbers. If I substitute this both into here, so n plus 1 also can be written. You see, from here I can say n plus 1 also can be written as p1 m1 plus j1, p2 m2 plus g2, and etc. Product p. For example, here let me take this same. I think like this, same L, and here L. So in that case, PL, PL, ML, M sub L plus J sub L, J sub L. So generally, this is the n plus 1 can be generated or can be expressed as a product of prime numbers. So that's why this is also generally good proof, but actually in other theorems they prove differently than this. Okay, but here our main aim, you know, how to apply the principle of mathematical induction. You see, for the principle of mathematical induction, pay attention. We have the two versions of that one. One is P1 is true and Pn is true, implies Pn plus 1 is true. Then Pn is true for all n. Second one, P1 is true, P1, P3, and Pn are all true, which implies Pn plus 1 is true. Then Pn is true for all n. Okay. But this example is not very straightforward example for this method. Okay. And here the remark says that the prime factors of n, prime factors, if the prime factors of n are p1, p2, pk, then there are natural numbers m1, m2, mk, such that, so actually this is a expressions. Any integer number can be expressed as a product of the prime numbers. Okay, this is a representation of n by the product of its prime factors. Here, of course, the arrangement P1 should be less than P2, P3, P2 less than P3, and PK. In the example also shown. So next definition. Okay, I will show some example from here. Actually, let me little show some proof of the problem. For example, all numbers of this are divisible by 5. By 5. How can I prove? You see, now we have already few ways of proof: direct method, indirect method, contrapositive method, negation method, and so on. Now we have the principle of mathematical induction. So let me just prove they use this mathematical induction for such kind of problems. This is example, maybe I can say 2. For all numbers of the form 7 to the power n minus 2 to the power n are divisible by 5. Okay, this is the statement. Now how to prove it? Proof. First, I will check when n equal to 1. So 7 to the power 1 minus 2 to the power 1, which is 5. 5 is divisible by 5. This is the P1 statement is true. N equal to 2. 7 to the power 2 minus 2 to the power 2, which is equal to, this is 49 minus 4, which is 45. This is P2 statement is also true. It can be written as a this 45 is divisible by 5. So you see, actually I cannot find counter example to this problem. So as we learned from the previous knowledge, so it might be conjecture. So now we need the proper proof. The other type of method is difficult to use here, but this mathematical the principle of mathematical induction is very good. Now what I say, so since n equal to 1 is true, n equal to 2 is true, P2, I assume let this assumption, the statement is true for n equal to, for example, k cases, okay, k cases, which is 2 to the power k minus 2 to the power k can be written as 5 times, let's say, m. You see? So all of them, you see, it can be written as 5 times some numbers. Now I need to prove when n equal to k plus 1, which is 7 to the power k plus 1 minus 2 to the k plus 1, okay? So k plus 1. You see, here little interesting techniques is needed to do. For example, you see, if I say like this one is 7 times 7 to the power k minus 2 to the power k. So how can I write as 5 times m? It cannot be seen. So that's why here what they put, they just subtract, you see, from 7 k plus 1, in my case k plus 1, minus 7 times 2 to the power k. They subtracted and added 2 power k and minus 2 to the power k plus 1. Then grouping. You see, here I can take out the 7. What I have here, 7 to the power k minus 2 to the power k. Okay? 7, okay, 2 power k plus, here I can take out 2. Yes, I can take out 2. So in that case, what I have, 7, 7 power, okay, plus 5, 7, okay, this one, 2n plus 1, okay, correct. This one, look, 2 to the power k, here I can just compute, this one I can compute, okay, 7 to the power k, here 2 to the power k times 2. So if I take out 2 to the power k, I have 7 minus 2. Okay, now 7 times 7 to the power k minus 2 power k is 5 times m plus here 5 times 2 to the power k, which is written as m1. You see, I take out the 5 and put all the other numbers as a m1. So it shows, you see, if the statement P1, P2, and PK are true, and PK plus 1, the statement is also true, you see, but we have to show this. We have to show. What happened? Sometimes it is like this. How to increase? Yeah. Okay. I hope you can see, but how to increase, I do not know. But now I think I just open the new one. Open the new one. Okay. Open the new one. Okay. Generally, you see how we can use such kind of the principle of mathematical induction to the problems. You see, for example, here, example 3, show that sinus n times x is less than n times sinus x. Again, we can use induction method. Okay, so please try to learn from. I will put this one. Let us prove one of this statement, which is exercise. Okay, from exercise I prove one. I think that's enough. Okay, still, even I use the strong one, the exercises, one point, for example, 2, okay, 1.2. So that proof 3 plus 11 plus n etc. plus 8n minus 5 is equal to 4n square minus n. All integer numbers for any n. Okay, proof. Okay, for n equal to 1, I will calculate the left side. So when n equal to 5, we have on the left side, we have only 3 because 8 times 1 minus 5 is 3. Only I have like this. And on the right side, n equal to 1, 4 minus 1 is 3. So P1 is true. So n equal to 2. N equal to 2. N equal to 2 means 3 plus 11 because n equal to 2, the 8 times 2, 16 minus 1, 11. 3 plus 11 equal to 4 times 2 square minus 2. Okay, this is 4. 4 times 4. 16 minus 2 is 14. This one also 14, this one also 14. The P2 is also true. Now we assume, so n equal to k, is also true, which means 3 plus 11 plus etc. Plus 8k minus 5 can be written 4k square minus k. So this one is true. Okay, this one up to here is true. Now for n equal to k plus 1, which is 3 plus 11 plus and etc. plus 8k minus 5 plus 8k plus 1 minus 5. Okay, so 5, we should derive the right side. Okay, now look, up to here we have this 4k square minus k plus 8k. I open up 8k plus 8 minus 5 is 3, right? Now if it is so, now I can say what? So 4k square minus plus 7k and minus 3. So this one I can say 4k plus 1 square. Look, 4k square plus 2k times 4k is 8k. Okay, 8k. I have 7k. 7k. So I have to subtract 1k. I have to subtract 1k. So this is 8k plus 1, 4. To be 3, 4 minus 1, right? Now I can write it as the right form. You see, this one I can write 4k plus 1 minus k plus 1. So this is the k plus 1 statement is true. So if k statement is true and k plus 1 is true, then I can make conclusion because of induction theorem. The pk is true, or pn I can say is true for all n from capital N. That is a proof, or that is the implementation of the mathematical induction, or principle of mathematical induction to the problems. You see, here, this again, as I told you, there are many good examples. Please play. This is actually, this part is only for the natural number. For the natural number, we have 10 problems, and for the set of Q, we have another problems. Okay, but now now I will go back to the main lectures, and here I want to give, what is the definition of the integer numbers. So first,
sorry, doctor, to interrupt.
What?
I have a question.
Very good, mashallah. Welcome.
For the previous theorem, the proof P2, the one.
You mean if from here?
The prime number proof.
This theorem.
This one.
Okay.
I do not understand why P2 is clearly true. Because because the statement is, if it is written in sentence, it says that 2 may be expressed as a product of prime numbers. But
Yes.
For what I understand about product means you got two. It's a binary operation. You have to multiply two numbers together in order to get one. So, but 2 is itself only. It just, I mean, 2 is don't have multiplied by something. It's just 2. So how is it like this statement will be true if I just say?
MashaAllah. Very good questions. Actually,
because
see, from
because if I write in 2 times 1 or 2 times 1 times 1, that one is actually does not satisfy the statement, right? Because 1 is not prime number as well. Yeah, that's my question.
Okay. As I understand this theorem, actually proof, as I told you, is not very proper proof. But after reading, I understand like this. Look, here statement state is, so n should be strictly greater than 1, right? Greater than 1. The any integer number, or actually not integer number, natural number, because integer number includes the negative. Here we are talking about the natural number greater than 1. Actually, here may be expressed. I can say can be expressed. Also, we can formulate express it as a product of prime numbers. So it means, so the any numbers P1, M1, P2, M2, and etc. PM. So here, how we call it? PK. I think beta PK. Yes, PK, MK. Actually, we should show, so any integer, the positive integer number can be expressed as a product of prime numbers. Actually, we have to show this. Okay, but they are not doing this way. So they say that to be proven this theorem, they do the assumption. You see, P2 is true, which means starting from n, starting from 2, 3, and so on. The any number. This, you see, why there P2? P2, I understand n started from the number 2, 2, 3, and so on. So this P of 2 means that n equal to 2 assumption is true. It is generally it is correct. When n equal to 2, you can easily see it can be expressed as a product of when n equal to 2. So 2 is written n equal 2 times 1. Actually, 1 is not included here. We just say 2 to the power 1. 2 to the power 1. So when n equal to 3, n equal to, this is the P2 assumption. N equal to 3, so 3 is equal to 3 to the power 1, because this is already prime numbers. There is no others. This is P3 assumption. So, for example, n equal to 4. I have 4 equal to 2 times 2, which is 2 square. You see, 2 is a prime number. M1 is a 2, so it can be written as a product of prime numbers. So this is P3, P4 statement. And assume that all P, N, Pn, actually here I can say N equal to like this, P1, M1, P2, M2. In general, I should say like this, Pn, Pk, not N, Pk, Mk. So this one is true. Now for the Pn plus 1, which is this n plus 1 also should be written as a product of this. Actually, if I properly show pk, not exactly pk, this is p1, p2, and not exactly same pk. Maybe I can say pl, ml, here L is greater than K. So if I show this way, then I can say that this proof is more proper proof. But here also good logically product proof is given. Now look, they are not showing this way. They are saying the n plus 1. You see that's why generally this proof is also acceptable. Can be written as a product of two integers. Both of them, k also less than n, and m is also less than n. Okay, less than n. If k less than n, according to the above assumption, then it means n equal to k. N equal to k, pk assumption is true, which means that the k is written as p1 to the m1, p2, m2, and etc. pk, mk. And for the n equal to m, pm is also true because from the above assumption up to pn it is true. So the m is also can be written similarly like this: p1, but not m1. Let's say l1, p2, l2, and etc. pk, l2, lk, lk. You see, when I substitute these two into here and take out the add this, look, n plus 1 from this p1 m1 plus l1, p2 m2 plus l2, the product pk mk plus lk. You see, so under this assumption, I can write n plus 1 is a product of prime numbers. Actually, this way more proper. I can say that this form of the proof, if you understand it, it is more proper. Did you understand now or not?
Doctor, so do you mean by product of prime numbers is just that its definition is the formula like this?
Yeah, so you see here, please pay attention. If n plus 1 is written as a product of two integer numbers, both of them should be less than n. You see, less than n. For the less than n, we have this expression. You see, we have this expression. That's why, so the n plus 1 also can be written as a product. I think after writing this form, I hope more clear picture. Here, just they stated n plus 1 is also product of primes. It cannot be seen. But from here, I can see it can be seen. Is it okay? Now, can you imagine now?
Sorry, doctor, but I still do not understand why 2 power of 1 is said to be a product of prime numbers.
Yeah, my friend, please pay attention. What is it? The prime numbers. Prime numbers is the numbers which has two dividers, itself and 1. So when n equal to 2, so it can be written 2 to the power 1 only.
Yes, but I do not understand why is it called product, because from what I understand, product means we have to multiply with two things.
Multiply.
But here is one thing only.
Yeah, but you know, if n is a prime, then this is the writing of prime numbers. When you see, for example, 4, I can write this number 2 times 2 also. I can, but
Yes, but I understand if more numbers than that, but I do not understand like 2, then 2 times what? 2 times nothing.
yeah, you see, as I told you, if n is already prime number, then we have only one number. For example, you know, if I say n equal to 100 and, for example, 13, I think there is no divider 130. 3, 4, 5. Yes, there is no. So if it is so, 113 is equal to 113 to the power 1. So P1 is this, M1 is 1. So that is a writing of prime numbers. So theorem says,
Then can
n,
we say that just one number itself, I mean like 2, 3, just one number can be said to be, it is a product of some numbers.
but for the large n, yes, you can see for the large n, but for the not only small n, large n also, as I told you, cannot be written as a product. You see, here, yes, we can write as a product, but as a power, also only one. Friend, you try to understand, you know, how to apply in the principle of mathematical induction to prove the problems. To prove the problems, it is said, if P1 is true, or let's say, you see here, P1 is not true. P2, starting from the P2 is true, P3 is true, and so on, Pn is true. Then for the Pn plus 1 is true based on the previous suggestion. If we are able to show it, then it is true. Then we can make conclusion. You see the theorem. Please pay attention. The structure. P1 is true, P1, P2, Pn is true, implies Pn plus 1 is true. Then Pn is true for all n. So we can make conclusion based on this principle. Okay, so that's why I told you the proof, for example, of this theorem is not very easily can see. But now I hope after my expressions in this form, you see, pk, pm, and substituting, then I can say, yes, the n plus 1 also can be written as a product of prime numbers. You see, of the product of prime numbers. But power, this is I can denote power m1 star, m2 star, and so on. It doesn't matter. So always we can write the product of prime numbers, any natural number can be written. So this is a proof, you know. There is no other type of proof. We have to assume, then derive. After assumption, we have to derive. Okay, friend. If you read once again and try to see this video, I hope you can understand my point. So this is a proof. Okay.
Doctor, I will try to watch and understand again later.
Even, you know, in the YouTube, you just search how to what is the proof of this theorem. You can see over there also. But this is my explanation. I hope this was more clear than here the proof. Now look, here there is another interesting point. For example, after introducing the integer number set, this is a definition. The set of integer denoted by z, and it is a subset of r defined by natural number 0 and minus n, n from z. This is the definition of integer number set. This is the definition of the rational number set. Now, this theorem, how we prove this theorem? You see, here we are not using the induction method. You see here, for proof of this theorem, we don't use induction theorem. Look, I hope the proof is properly given. Maybe some point you didn't catch. So this theorem, TH3.4, I don't write the all. So it is said that x squared equal to 2 has no solution in rational number set. Okay, actually from here, from mathematical point of view, we know it the plus minus square root of 2 plus 2 minus 2 is a solution of this equation. But plus 2 is not rational number. Minus square root of 2 is also not rational number. So this equation has no solution in the rational number set. Okay. Now how can I prove? Proof actually also very nice. Look. Here assumption, please. Suppose means it's an assumption. Suppose there is x from Q such that x square equal to 2. So we are supposing there is x in Q, this equality holds. Okay. Now if it holds, according to the definition of the Q, so x can be written as a over b. This is a rational number definition. So AB from the Z, but B cannot be equal to 0. Okay. So now if I substitute this one into there, A over B square equal to implies A square equal to 2B square. So what does it mean? This means the A has a multiplicity of 2. A has a multiplicity of 2. You see, A square equal to 2B square. Okay. Now, if I substitute this, after substitute A square equal to B square, from here, already I stated like this, 2B square, which implies 2 is a prime of the factor. 2 is a prime of prime factor, actually prime factor of A square, so it means A square has divisible number 2. So now another interesting point, therefore it is also prime factor. Now if it is so A can be written as, for example, 2m. If A square has a prime factor 2, so A can be written like this. So this one implies, okay, now 2B square, look, I'm writing from here, equal to A square. A square is 2m square, implies B square equal to 2m square. This one implies that B has such kind of 2 times, for example, L. Look, A has a factor, prime factor 2, prime factor 2. B also has a prime factor 2. So you see, number A and B has prime factor 2. Prime factor of 2, prime factor of 2. So it means that actually in the rational number set, so this A over B should have what we call it. Actually, after this, okay, look, conclude that is well product exception. No common factors. Okay, actually, in the rational number set, A and B shouldn't have common factor. In the rational number set, A and B A and B should not have common factor. But because of our wrong assumption, you see, because of our wrong assumption, we come up with the conclusion that A and B has common factor 2. So it is impossible. So if it is impossible, then our assumption is wrong. If assumption is wrong, then this equation has no solution in the form of ratio. So that is a proof of this theorem. Unfortunately, I couldn't reach these completeness axioms. Okay, no problem. This completeness axiom we have to study. We are almost completing. I think 1 hour in the next lecture I can complete. Please, mashallah, your question is very good. You know, it is better to ask questions during the time of the lecture, and you can break, no problem. But after that, please, you try to understand the main point. Actually, the here important one is the core point of the problems. How we approach, how we solve problems. Actually, solving problem is one. Proof is totally different. Actually, here everything we have to prove. So that's why as an example is not good. As an exercise, okay. Example can be written as a statement, as a preposition. So generally, for today, I think this one is enough. If you have any other type of problems, questions, you are welcome. But currently, I'm stopping at this point, okay? So, welcome. So, how many students left? 57 already. No problem, because now already 4 minutes extra. So, general idea is clear?
Yes, doctor.
Yes. Okay. In that case, please be ready. Next week on Monday, I will give the quiz, simple quiz, but you need the proof. One relates to the proof. One is a computing. Okay. Please be ready. Okay. If no questions, that's all for today. Thank you very much, and see you next Sunday.
Thank you, doctor.
Thank you.
Thank you very much, and bye bye.